5 and social media. So we're talking about a sample of 300 adult women who have looked at a picture of an X on social media 10 to 15 times per month. 180 of them admitted to it, so that gives us our p hat, which I'll jot down nice and big up at the top, of 0.6, so 60%. Says Cosmo published an article and they claim that 56% of women admit to doing this. So does our study indicate that the true proportion has increased? Okay, so we've got a 1 proportion z-test. We're testing this claim, so it's a z-test, not a z-interval. Okay, so my null is that p is still 0.56. My alternative, I'm wondering if my study showed, did that proportion go up? Yeah, so it has it increased. There we go. Okay, so I am not going to check the conditions. You guys can do that. You're experts at it now. But pretend I did over here. And we'll just assume you can calculate your test statistic. Again, this video is mostly just for you to check your answers, not necessarily a guided tour of Unit 5. So you should end up with a test statistic of 1.396 approximately, depending on how you rounded, which gives us a p-value of 0.081. Well, since our alpha was 0.05, 0.081 is bigger than alpha. So our p is not low, which means we will not reject. Let's go ahead and conclude that. Okay, so concluding, we fail to reject the null because 0.081 is greater than 0.05. P-value greater than alpha. Okay, so this means we have insufficient evidence. So we have not found anything unusual enough to prove the alternative. So we have insufficient evidence that the proportion of adult women who creep on their X has increased. Okay, paraphrasing here, of course, that's not what the actual problem said, but I don't want to type out the whole context. All right, so explain what the p-value means in context. Well, our p-value was 0.081. 0.081, so that means if the true proportion is 0.56, like Cosmo advertised, then there's a 8.1% chance that we'd see a sample proportion of 0.6 or more unusual. Okay. Construct a 90% confidence interval. Again, I'm going to assume that you can check your own conditions, and I'm going to try to keep this video nice and short. So the confidence interval you should have come up with is 0.55 approximately, depending on rounding, to 0.65 or 55% to 65%. So I'm 90% confident that the true proportion of women who look at pictures of their ex is between 55 and 65%. Does this conclusion from the confidence interval confirm or contradict your conclusion to the hypothesis test? So we'll see here, since 56, right, Cosmo's belief, since 56 is in that confidence interval, we again fail to reject. Let's type that up. So we fail to reject the null because 56% is in the confidence interval. Okay. And down here, what level of significance would match a 95% confidence level? So a 95% confidence level, if we sketch a picture, and this was a one-tail hypothesis test, right? We wanted to know had the proportion increased. So one tail, we were looking at the upper tail, which means all of this was my significance level, my alpha. So that means that alpha for a 95% confidence level would have been 0.025. Okay, explain type 1 error, type 2 error, and power. So type 1 error is we reject the null and the null was true. So type 1 is we say the proportion of women who look at pictures of their ex has increased, but it hasn't. We were wrong. Type 2 is the other way around. This is we don't say the proportion of women who look at pictures of their ex has increased, but it actually has. Okay, and finally power. This is the probability that we say the proportion has increased, and it actually has. So we were right. We rejected the null, and the null should have been rejected. That's what power is. Okay, so if I run this hypothesis test with a 10% significance level, so alpha is getting bigger. So imagine again that rejection region was at 5%. Well, I'm going to bump it up a little bit. And so now I want that rejection region to be 10%. So alpha went up. Alpha is type 1 error. That's what it is. And so if alpha goes up, then type 1 goes with it. Okay, if type 1 goes up, then type 2 goes down. And then finally, our power has increased. Right, so if we think back to power, this is the probability that we say the proportion has increased. So for me to say the proportion has increased, that means I have to get something in this shaded blue region. So the more space that blue region takes up, the more times I'm going to say the proportion has actually increased. So just naturally, the power is going to go up. Okay, suppose the new sample was taken with 620 adult women. Okay, so that means our n, which was 300, has gone up. So how does n increasing change all of these three things? So when n goes up, in general in statistics, n going up is good for your findings. It provides you with a better idea of the true population in general. And so keeping that in mind, if n goes up, then power goes up. So I feel like that's the one that's most intuitive. Power is a good thing. We want to reject the null when the null should be rejected. So when we think of power as 1 minus beta, and when we think of type 2 as beta, well, when this number is getting bigger and bigger and bigger, then this beta must be getting smaller. Okay? And lastly, type 1. Well, if we read the rest of this problem, we'd see that alpha stayed the same. So I had the same level of significance. So alpha stays the same. Again, alpha is type 1, so if alpha stays the same, type 1 stays the same. All right, part I, you decide to conduct another study, a simple random sample of 800 high school girls, and 496 of them admit to watching or looking at pictures of their ex. Okay, so what we have here, I'm going to call the proportion of older women was 0.6, and the proportion of younger women turns out to be 0.62. Okay, so those will just be my notations for these two groups, and I would probably want to define that over here, but I'm not going to because you guys just heard me define it out loud, but on your paper you would want to just write it out. Okay, so I saw this sample of older women and I saw this sample of younger women. So I saw that younger women were 2% more likely to look at pictures of their ex. Well, is that significant? That's what we're going to test. So I want to know, I think these groups are going to be the same because that would be boring and uninteresting, and that's what your null is supposed to be. And I'm wondering if in fact they're different. So I know this one's going to be two-tailed because it says, is there a significant difference? So it doesn't say test one is greater than the other or whatever. Okay, so with that in mind, we run the two-tailed hypothesis test and we end up with a z of negative 0.607 and a corresponding p-value of 0.544. Okay, so if I'm running this at a 5% significance level, I want to compare that p-value to alpha. P is much, much bigger than alpha. 0.54 blows 0.05 out of the water. So for this, we would again fail to reject. So fail to reject the null because p-value greater than alpha. And if you compared it, then that's fine, but if you didn't, then I'd probably include it down here. So we have insufficient evidence that there's an actual difference. And so I'm saying that that 2% difference that we saw was just chance. So we have insufficient evidence explain what p-value means. So p-value is, again, if the null is true, what was the probability that I would see something that unusual? So if there really isn't a difference between the proportion of older women that creep on their ex and younger women that do the same, then the chances, or then there's a 54.4% chance, 54.4% chance of seeing a sample difference of 0.02 or more unusual. Okay, so I'll kind of talk a little more about that. So what this is saying is if the null is true, so if there truly isn't a difference between high school women proportion and the adult women's proportion, then the chances of seeing this specific sample and this specific sample and getting this specific sample difference, the chances of seeing that, well, there's a 54% chance of seeing that. That's pretty good. That's going to happen about half the time. So that's not really that interesting. So we fail to reject. And then finally create a 95% confidence interval. Our 95% confidence interval, we've got to check those conditions. We've got to label the X1, the N1, the X2, the N2, all that fun stuff for your actual work. I'm going to trust that you can do that and check with you guys on Tuesday when you finish your posters. And as far as the answer goes, here's what you should have come up with. -8% to 4%. And so this confirms what our hypothesis test just did, that it's possible that there isn't a difference, that P naught, or that P of the older women is the same as P of the younger women. And so we're 95% confident that the true difference in the proportion of older women and younger women is between -8 and 4%. And that would be the interpretation for your confidence interval.